Welcome to this comprehensive YouTube tutorial on two fundamental concepts in electrical engineering. In this tutorial, we will demystify Thevenin's theorem and Norton's theorem, breaking down the principles, applications, and practical implementation. Whether you are a student striving to ace your electrical engineering exam, or you are a curious DIY enthusiast looking to enhance your understanding of circuits, this tutorial will equip you with the knowledge and skills you need. So let's dive in and unravel the secrets of Thevenin and Norton's theorem. Now that we have been introduced to source transformation and superposition principle in our last two YouTube tutorials, it is possible that we develop two more techniques that will greatly simplify the analysis of many linear circuits. The first one is the Thevenin equivalent circuit, and the second one is the Norton equivalent circuit. Let us suppose that we need to make only a partial analysis of a circuit. For example, perhaps we need to determine the current, the voltage, the power delivered to a single load, that is a single resistor, by the remainder of the circuit, which may consist of a sizable number of sources and resistors. Or perhaps we wish to find the response for different values of the load resistance. So the Thevenin's theorem tells us that it is possible to replace everything except the load resistor with an independent voltage source in series with a resistor. I was saying this in the last tutorial that one of the consequences of source transformation is to make us simplify to Thevenin's and Norton's theorem. That is, we want to convert a circuit into just a voltage source in series with a resistor. So that's Thevenin's theorem. It tells us that it is possible for us to replace everything except the load resistor with an independent voltage source in series with a resistor. I'll give an example diagrammatically very soon. And the response measured at the load resistor will be unchanged. But the Norton's theorem, it tells us that we can obtain an equivalent composed of an independent current source in parallel with a resistor. Then when I was telling us about source transformation, I was saying that we can interchange between Thevenin and Norton. I said we can interchange between voltage source and current source. That is, we can transform a source to another. So, and I told you that a voltage source must be in series with the resistor before you can transform it. So it's just like we can transform the Thevenin's equivalent circuit to Norton equivalent circuit. In this case too, it means that we are converting a voltage source in series with the resistor to a current source in parallel with the resistor. For example, let's say we have a complex network. So I'll just replace the complex network with this block, and I'll name it a complex network. Right, and it is connected, just like I said, to a load resistor, which is RL. So what Thevenin's theorem is saying is that it is possible for us to convert this complex network. It is possible for us to replace this complex network with a voltage source in series with a resistor. That is, we have a resistor and it is in series with a voltage source. So we've replaced the complex network with a voltage source in series with a resistor, and of course the load resistor is still here. So this is the Thevenin's equivalent voltage, and this is the Thevenin's equivalent resistance RTH, and of course this is the load resistor. And the Norton's equivalent circuit is telling us that it is possible for us to replace this complex network with a current source in parallel with a resistor. And I can tell you that we can convert this Thevenin, this is Thevenin, right, to Norton. How do we do that? By source transformation. So what do we have? So we have a current source, right, in parallel with a resistor. So we replace the complex network. We've replaced the complex network with a current source in parallel with a resistor. So this is the Norton. I'll call it IN, and this is the equivalent resistance. Then this is the load resistor, which is RL. Right, so this is the Norton equivalent circuit. The Norton equivalent circuit. That is very, very simple. So if we get the Norton, right, we can convert to the Thevenin equivalent circuit by source transformation. So one of the main uses of Thevenin's Norton's theorem is the replacement of a larger part of a circuit. It is often a complicated and uninteresting part with a very simple equivalent. The new simpler circuit enables us to make rapid calculations of voltage, current, and power which the original circuit is able to deliver to the load. It also helps us to choose the best value of the load resistance. In a transistor power amplifier now, for example, the Thevenin and Norton equivalent enables us to determine the maximum power that can be taken from the amplifier and delivered to the speakers. So, let me give us an example of this. I will still talk about maximum power transfer very, very soon. This is the example that will be used to explaining the Thevenin equivalent circuit. Right? Steps for the Thevenin's theorem. Given any linear circuit, rearrange it in the form of two networks, A and B, connected by two wires. So this is network A, this is network B. Network A is the one on the left, network B contains the load resistor. The second step is disconnect the network B, right? Let us disconnect this. So when we disconnect this, what do we have? We have the 3 ohm resistor here. So I'm only drawing network A. So network A ends here, right? And I have the 12 volts voltage source ends here, and I have 6 ohms here, right? 6 ohms, 7 ohms, 3 ohms, and I have 12 volts, right? So I've disconnected network B. So I want to get the equivalent for this network. Equivalent. So to get the equivalent for this network, turn off or zero out every independent source in network A to form an inactive network. Remember that active components are what are sources. So once you turn off the source, it means that the rest of the components you have are just resistors, and which are passive devices. So we have a passive network. So turn off the independent source, and of course calculate the the RTH. That is, calculate the Thevenin equivalent resistance. So listen to this very well. To get your Thevenin equivalent resistance, you turn off the independent source in network A to form an inactive source. If there is a dependent source, leave the dependent sources unchanged. Don't turn off the dependent sources. Dependent sources are the one that they have diamond shape, right? They have diamond shapes. So what do we do? Once you turn off this, remember, for a voltage source, if you want to turn it off, you turn it to a short circuit. If it is a current source, you open it, it will turn to an open circuit. So what do we have? We have 3 ohms, right? We have 3 ohms, 3 ohms here, 7 ohms here. Then we still have 6 ohms here, 6 ohms, 7 ohms, and we have 3 ohms. So what is the RTH? RTH what? It will be 3 is parallel to 6, then it is in series with 7. Am I right? That's it. 3 is parallel to 6 in series with 7. So what do we have? 3 parallel to 6 was 3 times 6 over 3 plus 6, then plus 7. That will give me 9 ohms. So my Thevenin equivalent resistance is 9 ohms. right? So how do I get voltage, a Thevenin equivalent voltage? So what I will do is I will simplify this circuit using the methods we've learnt before. So, and I would like to use source transformation, because I was already saying it in the last tutorial that the consequence of source transformation is the Thevenin and Norton theorem. So here, source transformation will help me simplify the circuit to a Thevenin equivalence network. This is one way of getting your Thevenin equivalent resistance. So using source transformation, what will I do? I will convert this source to a current source, so that these 3 ohms will now be in parallel with 6 ohms, right? So that I can combine it together. So if I do that, what will I have? I will have a current source in parallel with the 3 ohm resistor. Then there's also a 6 ohm resistor in parallel to that. Then before we now have a 7 ohm resistor, right? So this is 7 ohms, 6 ohms, 3 ohms, and of course by source transformation we have 12 over 3, which is the current, right? So it is equals to 4 amperes. So this is 4 amperes, right? So that is it. So when we combine 3 and 6, what do we have? We have 2 ohms. 3 times 6 over 3 plus 6 will give me 2 ohms, right? So what I do that, what will I have? I will have 4 amperes in parallel with 2 ohms. Then it say this one is in series, which is the 7 ohm resistor. The 7 ohm resistor, this is 2 ohms, and this is still 4 amperes, right? So I will now do source transformation again. Once I convert this back to a voltage source, what will I have? V is equals to IR, right, which is equals to 4 times 2, which is equals to 8 volts. So what will I have? I will have 8 volts here, then 2 ohms here. It has become series now. Remember, when you transform to a voltage source, we have a voltage source in series with the resistor. So 2 ohms here, 7 ohms here, and this is 8 volts. So 2 ohms and 7 ohms, they are in series, right? So the network A has been reduced to a Thevenin equivalent voltage. And don't forget, this is a voltage source, so it should be plus minus 8 volts, and we have 9 ohms here. So this is 9 ohms. So this is the Thevenin equivalent circuit. The Thevenin equivalent. Remember, the Thevenin equivalent says that it is possible to replace a circuit, a complex network, with just a voltage source in series with the resistor, right? So, and this is what we have done to reduce that circuit to that. So this is just network A. So when we connect back our network B, which is a load resistor, what do we have? We have RL here. So this is circuit. So of course we can get anything that is connected to this RL. So how do I get the power on RL? That's straightforward, right? So power is what? Power is equals to current times voltage, right? Which means that I need to know the current here going through RL, and I need to know the voltage drop on RL. Or power is still same thing as I squared R. That is, once I know the current flowing through RL, that's all for me. And this R here is the load resistor. So how do I get the current going through RL? So just by simple Ohm's law. That is, the current going through this single loop is what? V over I. That is, the current going through this single loop is V over R, the total resistance. So if we are to convert the circuit to a Norton equivalent circuit, what do we have? The Thevenin equivalent circuit is this. We have 8 volts here, and of course we have the load resistor here, RL, and of course this is the network. This is 8 volts and this is 9 ohms. This is the Thevenin theorem, the Thevenin network. So to convert to Norton network, what do you do? Source transformation. That is I what is equals to V over R, which is what 8 over 9 amperes. So if we do this 8 over 9 amperes, let's say we want to calculate the current in this circuit. Now what do you do? We say 8 over 9 plus RL, right? So what will give us 8 over 9? It is when RL is equal to 0. So which means that that's the maximum current that can flow through RL, right? 8 over 9 amperes. So if you draw the Norton equivalent circuit, we have the current source here, right? So we have the resistor and we have the load resistor. This is 9 ohms RL and this is 8 over 9 amperes, and of course this is the Norton equivalent circuit. Do you understand? If you don't understand what I've explained, please you can drop a comment on this tutorial and I will make sure I give you an answer. So let's do one more example. This is another example to explain how to get the Thevenin and the Norton equivalent circuit of a network. So the question says that we should find the Thevenin and the Norton equivalent circuits for the network faced by the 1 kilo ohm resistor. What does that mean? It means that the 1 kilo ohm resistor is our load resistor. The 1 kilo ohm resistor is our load resistor, right? RL. So the first step is that we cut it out, and that's what I've done. So which means that we will have to simplify this into Thevenin and Norton, right? So what do we do? By simple analysis, we can see that we can apply source transformation. So let's apply source transformation. So by applying source transformation, I'll convert this to a current source, right? So what do I have? So current source is what? I is equals to V over R. So which is what? 4 over 2 kilo ohms. 2 kilo ohms is 2000. What does that give me? That's 2 milliamperes. So if I draw that, this is the current source parallel to 2 kilo ohm resistor, then parallel to another 2 milliampere current source, then the load resistor. So we have 3 kilo ohms here, we have 2 milliamperes here, we have 2 kilo ohms here, then we also have 2 milliamperes, our transformed source. So in our earlier tutorials, I explained how to combine sources. So we have two current sources and both of them are facing upward. What does that mean? It means that we are adding them together. So when we add them together, what do we have? We have 2 plus 2, which is what? 4 milliamperes. So I have 4 milliamperes here, right? So I have 3 kilo ohms here, and of course the load resistor, which is 1 kilo ohm. Then don't forget our resistor here. which is 2 kilo ohms, 3 kilo ohms, 1 kilo ohm. Always separate this. This is our load resistor so that you won't be confused. And from here now, it's very, very simple. Transform it back to voltage source. Transform this back to voltage source. So what do we have? We have 2 kilo ohms here, and we have 3 kilo ohms here. Then the load resistor, right? Then if you transform that back to voltage source, so what do we have? V is equals to IR, so which gives us 4 milliamperes multiplied by 2 kilo, so that will give us 8 volts. So basically we have 8 volts here. Eight volts, 2 kilo ohms, 3 kilo ohms, and of course our load resistor, which is 1 kilo ohm. Okay, so the last step is let's draw our Thevenin by combining these two resistors. So when we combine the two resistors, we get our Thevenin equivalent circuit. So our Thevenin equivalent circuit is what? 8 volts voltage source in series with 5 kilo ohm resistor. So this is 5 kilo ohm and this is 8 volts. You can see that we've replaced the network with just a voltage source in series with a resistor. Right? So this is our Thevenin circuit. Thevenin. So if you are to convert that to Norton, what do we have? Source transformation, that is I is equals to V over R, which is what? 8 over 5,000. So what does that give us? 1.6 milliamperes. Right? So if I should draw that, we have a current source here, then of course the load resistor here, which is 1 kilo ohm, then I have 5 kilo ohms here, then of course the current source, which is 1.6 milliamperes. So this is a Norton network. So what is VTH? VTH is equals to 8 volts. What is the Norton current? Norton current is 1.6 milliamperes. And what is the Thevenin resistance? And I should tell you that Thevenin resistance is always equals to the Norton resistance, which is 5 kilo ohms. So this is our result. You can see that it is very, very simple to analyze. So that is just how to simplify a circuit, reduce a complex circuit to a voltage source in series with a resistor or a current source in parallel with a resistor. I should tell you that it is not only source transformation you can apply. You can apply any method we've done before. You can apply KVL or KCL to get your voltage source, and of course even to get your resistance. You turn off the sources, you combine the resistors, and that's how you get your Thevenin equivalent resistance or your Norton equivalent resistance. That is as straightforward as that. So what if we want to apply superposition? Let's apply superposition. So what does that mean? It means that we want to see the contribution of each source. We want to see the contribution of each source to to the load resistor, right? So if we perform superposition, that is, we draw two circuits because we have two sources, and we turn off one in each circuit. So if you are drawing, if you want to get the contribution of the 4 volt voltage source, we open the current source. If you want to get the contribution of the 2 milliampere current source, we short the voltage source. So let's draw the circuit for the two. So current source, opening the current source, or the current source contribution, the current source contribution is, we short the voltage source, right? Then we have 2 kilo ohms here, 3 kilo ohms here, then 1 kilo ohm. Then we have the current source here. So this 2 kilo ohm, 3 kilo ohm, and this is the load resistor, 1 kilo ohm, and this is 2 milliamperes. So we have 2 milliampere in parallel with 2 kilo ohms, and also in parallel with 4 kilo ohm, because the combination of 3 kilo ohm and 1 kilo ohm is what? 4 kilo ohm. So which means that I want to get the current flowing through 1 kilo ohm, right? So what do? Very simple, current division. Applying current division, because that's what I'm looking for. I want to see the current that is faced by what? The 1 kilo ohm resistor. That's what the question asks us to do. Current division rule. So what do I get? I have what? 2 over what? 2 plus 4 multiplied by 2 milliamperes. So what that give me? 2 over 6 multiplied by 2 milliamperes. So which means that the IN is what? 4. That's 2 over 3 milliamperes, right? So like I said, we put this one as IN prime. So let's get the contribution for the voltage source from the voltage source. Which means that we are going to open the current source. So we have the 4 volts here, 2 kilo ohms, 3 kilo ohms, 1 kilo ohm. So we've opened the current source. So this 2 kilo ohm, 3 kilo ohms, and this is 1 kilo ohm, plus or minus 4 volts, right? I want to get what? IN prime prime. So what would that give me? I can get the voltage through 1 kilo ohm first by doing voltage division, right? Applying voltage division, the voltage division rule. So the voltage division rule states that we should have 1 over 1 plus 2 plus 3, everything multiplied by 4, right? Vn prime prime, or Vth prime prime. Let me just use Vn prime prime. That's 4 over 6, which is what? 2 over 3 voltage, right? Sorry, this 1 over 6, right? That's 4 over 6, that's 2 over 3 volts, right? So if I want to get IN prime prime, that's Ohm's law, right? That's Ohm's law. Ohm's law states that we have Vn prime prime over what? 1 kilo ohm. So what does that give me? That gives what? 2 over 3 divided by 1000. So that's 2 over 3 milliamperes. So let us apply superposition to the circuit, which means that I want to get the contribution of the sources, the independent sources in the circuit. So look at it. We have what? We have two independent sources, the 4 voltage source and the 2 milliamperes current source. So, and of course, the first step is always to disconnect the load resistor. So let us do that and let us shut off one. So let us get the contribution, what? The contribution of the voltage source. So the voltage source contribution. Right, so the voltage source contribution, which means that we have to shut off, we have to open the current source. And remember that when we open the current source, we have this. This is already open, so no current flows here. And remember that because we've disconnected the load resistor, no current will be flowing here too. 3 ohms and 2 ohms. So we want to get the voltage that is being faced here. Let me call it VOC. Right, this plus minus 4 volts. So looking at this circuit, no current flows through 3 ohms, and therefore the voltage drop on 3 ohms is 0. Because of this open circuit too, no current flows through 2 ohms, and the voltage drop on 2 ohms is 0. What does that mean? It means that the VOC is what? Is equals to 4 volts. So let's now get the contribution of the current source. Right, so which means that we're going to short the voltage source. Right, so we still have the 2 ohm here, then we have a current source. And also remember there is 3 ohm here, right? But there's no voltage drop on it because it's an open circuit. It's series to an open circuit. So the 3 ohm resistor, there's no voltage drop on it, and then no current is flowing through it. Then we have a 2 milliampere current source here. 2 milliamperes current source. Then we have 2 ohms here, right? 2 kilo ohms. Sorry, the former board wasn't writing very well, so I had to change the board. So I want to draw the voltage source circuit. So right, so that is the contribution of the voltage source, which is this. Then the contribution of the current source, so which means that we are shorting off the 4 volts source, right? We still have 2 kilo ohms here, and we have 3 kilo ohms here. It's an open circuit because we've disconnected the load resistor. Then we have the current source here, which is 2 milliamperes, and this is 2 kilo ohms. So like I said earlier, that the 3 kilo ohms won't have a voltage drop, right? The 2 kilo ohms, it won't have a voltage drop. The 3 kilo ohms won't have a voltage drop because it's series to an open circuit. But right now, to get our V here, prime, so what do we have? The voltage that is on this combination. So and how do I get the voltage on the combination? This is the resistor, this is the current. So it's a single loop because nothing is coming here. Any current that is coming here is just going through this single loop. So what does that mean? We have IR, which is 2 milliamperes multiplied by 2 kilo ohms. So if you have V prime is what? 4 volts. So what is our VTH? VTH by superposition, what does that mean? It means that we are adding the response of each source to each other, right? So which means we have 4 volts plus 4 volts, which is what? 8 volts. And of course, to get RTH, what do? You turn off all sources. To get RTH, you turn off all sources. So when you turn off all sources, what do you have? You have this 2 kilo ohm, then 3 kilo ohm, right? This is a short circuit, and this is it. You have 2 kilo ohms here, and you have 3 kilo ohms here. So when you combine the resistors after turning off the circuit, this is an open circuit for current, right? So when you combine the resistors, it will be 2 plus 3, that's 5 kilo ohms, and that's it. So, and of course, you can now draw your circuit, and you can see that it's very, very simple to get the Thevenin's equivalent circuit and the Norton equivalent circuit. I used 2 methods here, the superposition method and the source transformation method. So you can use any method of analysis to get your Thevenin equivalent circuit and Norton equivalent circuit. So lastly, the Thevenin equivalent circuit is a way of replacing a complex network to just a voltage source in series with a resistor, and the Norton equivalent circuit is a way or a method of replacing a complex network with a current source in parallel with a resistor, and we can interchange or transform the Thevenin to the Norton by applying source transformation. It's just as simple as that. If you have any question of what I've touched so far, please drop a comment on the comment section and I'll give you an answer. Thank you very, very much. In the next section, we'll be talking about maximum power transfer and the Y delta transformation. See you in the next section.